Good evening. Cal here from Cal Academy. Today I'm here to talk about the second problem, which is detecting a loop in a linked list. You've already heard about it. Probably you already know how to solve it, but let's just do it together and understand the math behind it that makes the solution work. So without any delay, let's jump directly into our problem. So here is my whiteboard. Jump into that. I already have a linked list drawn out for you. So there's two parts to this problem. The first part of the problem is to detect if there is a loop. All right, let's do that first. And then once we are done with it, the second problem or the second part of the problem is to identify where the loop is, right? So identify the loop, basically. I'll just say that. So let's take this one step at a time. To solve the first part of the problem, if there is a loop, to solve this problem, I'm going to take 2 pointers. One is called the slow pointer, another one is a fast pointer. See, majority of the time when you deal with a linked list problem, this is always a clue, right? The slow and the fast pointers. So keep that in your mind as a tip or a trick when you deal with linked list. You're going to see how it helps if you've never run into that before, so you'll understand why it's super important to think about it. Let's say I have 2 pointers, slow and fast, both starting at the head, right? So this is your head pointer. Now, the definition of this is the slow is going to move 1 step at a time. The fast is going to move 2 steps at a time. That's pretty much it, right? So when I do this, the way I'm going to help answer this question if there is a loop is that when slow meets the fast. So this is pretty much how it goes, right? If I think about the pseudocode for this, right? So you have 2 pointers, the slow pointer and the fast pointer, both starting at the head. All right. And then you basically say either one of 2 reasons when you could quit this program. One is either the fast reaches null, because as you can see that the definition of a fast is it is 2 times faster than the slow, right? So that means the fast is the one that is going to hit the null pointer if this was not a looped linked list. So let's imagine I have a linked list like this, which is not a circular linked list, right? So if I now have this, and this is my null pointer, let's assume that. Now if I have a slow and a fast pointer, and if my slow pointer is going to move 1 step, so this is my slow, my fast is going to be 1, 2 right here. Then the next time slow is going to be here, the fast is going to be 1, 2, and it's out the way, right? So as you can see, the fast is the one that is going to reach the null before the slow does. So your pseudocode goes like that. Once you initialize your pointers and after you handle all the exit or the base cases, now what you need to think about it is that until the fast is null, until the fast reaches null, right? Either that condition is true or your slow meets the fast, all right? This is a condition that tells you whether your linked list is going to form a loop or not, whereas this condition tells you that it is not a loop, right? So you saw how this is true by the second example, but let's take a look at this guy. So going back to my first linked list here, now imagine this is my slow pointer, and both of my pointers starting at the head. Now my slow is going to move 1 step, my fast is going to be 1, 2. Now my slow is going to be here, now my fast is 1, 2. Now here is my slow, my fast is 1, 2. You see that? Now my slow gets here, my fast is going to be 1 and 2. So as you can see, both my slow and my fast pointers are going to be meeting here. You get that right? So as you can see, because there is a loop in here, your slow and fast will eventually meet within this loop. So that's why you have to check for one of these 2 conditions. Has my fast reached null already? If so, then I can easily go back and say that it is not a loop. Or if my fast hasn't reached null yet, but my slow meets my fast, then it is a loop. You got that right? So really, you see, the problem in itself is not super hard once you know this trick. Once you know the slow and the fast pointer trick, then you're done. Your problem is already done. To answer the first part of the question I meant to say, okay? Hopefully you understood that. Now let's focus on the second part, which is really the most interesting part of this problem. Now the question here is, can you help identify where the loop or where the circle meets? So as you can see in this linked list that I've given you, the circle meets at 3. Is that right? So the question is, how do you identify that loop? Obviously, if you're thinking about external data structures, then you can think about dictionary as one option. I'm not going to cover that today. I'm just going to go straight to the answer, or the most efficient answer to this solution, without using an extra data structure, all right? So let's see how we do that. So you see where my slow and fast met? When we decided that it is a loop, that was right at the 5. This is super important thing. Keeping in mind as to going through the first part of the problem, figuring out where your slow and fast meets, and then solving for the second part of the problem. Now here is what I'm going to do. I'm going to take one of these pointers away from here, and I'm going to put it back at the start. So it goes like this. So I'm going to take my slow pointer away, okay, and I'm going to put it back here. So now my fast is not here anymore. All right. So my slow is my fast is here, and my slow is here. Now what's going to happen is both of these pointers are going to move in the same lockstep together, meaning my slow is going to move here, my fast is going to move one step, not two steps. Now both pointers are going to act exactly the same. Now guess what? My slow is going to come here, my fast, which was here, now comes here. So you see exactly the slow and the fast is bound to meet where the circle meets. That is the part of the problem I am more fascinated about to talk to you, is to say, how did that work, right? But just to recap as to what we did, first, to answer the first part of the question, you have a loop that says until my fast reaches null, or my slow is not equal to, or until my fast reaches null or my slow equal to fast. Basically, you're going to move slow one step, right? And you're going to move the fast two steps. Then when one of these two conditions, when one of these two conditions is met, then accordingly you make the choice. Now for the second part of the problem, this is the first part of the problem. The second part of the problem, you're going to leave this the slow pointer back at the head, but leave the fast pointer where it is and move both one step at a time, right? And when you do that, it is guaranteed to meet at the point of the circle. Okay, got it? That is really it. This is the answer. But what I'm going to talk to you about is, how did that second part of the solution work? What is the magic behind it? So let me do this. I'm going to take a new window here. Give me a second. All right. So I'll just won't save it. I'll just create a new one. Okay. So now let's put the linked list back here. Okay. So here was my linked list that I used before. So I'm just going to draw the same one again, such that we are consistent with our problem. There we go. This was 1, 2, 3, 4, 5, and 6, and that is my head pointer. Okay. So if you remember, my slow and fast both met here. You got it right. So you got to remember that. And then once it did, I put the slow back here, and then they both went at the same lockstep. I meant to say. So how did the second part of the solution work? This is the math I'm going to explain. Let's assume we're going to put some variables around this mix. Let's call this distance as the x, the distance from the beginning of the head until where the circle meets as a distance of x. Then I'm going to have this distance from the point of the circle to all the way to where the slow and the fast eventually met in the circle as y. All right. Now I'm going to have this distance, the point in the circle where it met, to back to the circle. I'm going to call it as z. So I just have three variables, x, y, and z. Now what we're going to do is we're going to define, basically we're going to define a formula based on these three variables. So let's do this. It's a distance formula we're going to start defining. What is the distance traveled by the slow, right? If you recall, when I went and solved the first part of the problem, the first part of the problem is really what I'm trying to tackle here. To answer if there was a loop, right? How far did the slow have to travel or had to travel to meet with the fast? It traveled the distance of x, yes? And then it traveled the distance of y, because this is where the slow and the fast met during our first problem. Did you get it, right? So it's basically x plus y. Now, during the same time, what was the distance traveled by the fast? The fast also traveled the distance of x, because they both started at the head. Recall that. So the fast traveled at the distance of x, It also traveled the distance of y, right? But remember, fast was twice as fast as slow, right? So the fast went through this loop one more time. So you can see that the fast did go through z once. This was all during the first part of the problem, right? So when it went through x, then the fast went through the y, and meanwhile the slow was just coming through together, and then the fast went through z, and then it went through one more y to finally meet the slow and the fast here. So this was the distance traveled by the fast. Now, if I kind of simplify this, you can see that it is x plus 2y plus z. You get that right? Now, what I'm going to do is I'm going to equate the left-hand sides together in such a way that they are on the same units. So in other words, what is the distance traveled by fast? It is, according to our definitions, 2 times distance traveled by slow. Right? That was my definition when I started this problem. So now what's going to happen is I'm going to just put these formulas in place. So you see, what is distance traveled by fast? So it is x plus 2y plus z is equal to 2 times ds, which is x plus y. Now let's just do this algebra. So it's x plus 2y plus z is equal to 2x plus 2y. Now you can see what's going to happen. The 2y and the 2y gets canceled out. One of this x and one of this x cancels out. So what do I end up getting? Basically, z equal to x. So what did I just prove? What does it, how does this make any sense? So what we just proved is x is equal to z. In other words, we just said that this distance will be same as this distance here. So now you see what's happening? That is exactly why when I now solved for the second part of the problem, I said, let's take one of these pointers away from here, put it back at the head, and make them walk in the same lockstep together. When they do, you're guaranteed mathematically that this distance will be same as this distance, and hence you will know that they both will meet at the point of the circle. Isn't that neat? All right. I hope you learned something from here. This is why I love this problem. It's such a fascinating problem, but very simple algebra here. All right. Until next time, goodbye.